This is a lecture on pKa, and I'm going to give you the definition and show you where the pKa value comes from. The pKa value is a constant, and every carboxylic acid has its own unique constant, and therefore you can use it to identify an acid just like you can use melting point. So let's start with understanding what an acid really means. An acid just means that when you take a substance and you put it in water, if that substance releases or donates a proton to water, then that is an acid. And a strong acid, like hydrochloric acid, when we place it in water, it will donate 100% of its proton to water, and therefore none of this will remain. It will 100% become H3O+. When we have a weak acid, things are different, and all carboxylic acids are typically very weak. When it reacts and you place it in water, it will donate a proton, but it will only donate a lower percentage of it. For example, typically carboxylic acids will only donate about 3 to 10% of its proton to make this. So we'll have 3 to 10% here, and then we'll have 90 to 97% remaining as the carboxylic acid. Okay, so that's an equilibrium when we have that situation where it's not complete. That is called an equilibrium. And we have what we call an equilibrium expression. And in the equilibrium expression, we can say that K, and it's called Ka for, because this is the acidity equilibrium constant. So it's the K constant, but it's an acidity K constant, so we call it Ka. And it's simply just a molarity ratio of products over reactants. And what I mean by molarity is we take the products, so from that equilibrium, the products are RCO2 minus and H3O plus, and those are products, so we put them up here. And these brackets means that they are given in molarity concentrations, in moles per liter concentrations. That's what these brackets mean. And then our reactant. And notice that water was not included. When we have equilibriums, pure liquids and pure solids are never included in the equilibrium. So this is our equilibrium expression. Now, if we move on to do a little algebra, first I'm going to start by telling you about the algebraic function called P. And P simply stands for minus the log. P simply stands for minus the log. Now let's do the algebra. I can rearrange that equilibrium expression and isolate H3O plus. And then we would have this. Okay? And then if I took minus the log of H3O plus, then minus the log of the Ka, and this is just a little algebra. When you take minus the log of something times another, then it's minus the log and minus the log of the other part of the factor. Okay, so that's just a little bit of algebra. We'll also now replace minus the log with our P, indicating that that's the function in place. So that's pH is equal to pKa, And if I change the sign in front of minus log to plus, I can do that by just inverting these two components. And that's what we did. And this is our expression for the relationship between pH and pKa. All right, now once we have that relationship, pH will equal pKa if this piece winds up being 0. This piece will equal 0 if the RCO2 minus and RCO2H are equal, because that would become 1 and the log of 1 is 0. So when is this special case going to occur? When we do a titration of an acid, if we titrate our carboxylic acid with sodium hydroxide, it would look like this. And so during the titration of your acid, the concentration of your acid and the conjugate would be exactly equal at the halfway point. So halfway during a titration of your carboxylic acid, these two quantities will be equal, and therefore we would have the occurrence of pH equaling pKa, or the pKa value equaling the pH at halfway during the titration. All right, so now let's look at titration data. So first, let's look at what a titration curve is going to look like. As you add milliliters of sodium hydroxide and we measure the pH with the pH meter at the same time, it would appear like this. The more milliliters, the more milliliters, the more milliliters, and eventually, once all of our acid is about to be neutralized, we will get a rise in the pH, a rise until we get to a completely basic solution at high pH. Now, this point is called the inflection point. That is also the end point. That is at the point when we have precisely neutralized all of the carboxylic acid. And if we know the precise volume at the end point, then there are things that we can do with this. Well, one, if we know the volume, we can now figure out the halfway point, because we'd simply go back to 1/2 the volume of the endpoint, and that would be the halfway point. And if we could take and go up to our curve, and at that halfway point, pKa is equal to our pH. To determine the pH, we simply draw a line straight over to our pH axis, and it is at that point that now we would know our pKa. This is the halfway point, and at that point, pKa is just equal to the pH on the curve. So that's a very simple thing. We could do this the old-fashioned way, which is to just print out the curve, determine the inflection point, get the volume, go to the 1/2 point, come up to the graph, and draw a straight line over. And that's the way that certainly you can do it from the graph itself, but we have a technical way of getting to the end point. If we take the first derivative, which is the change in pH over the change in volume, which is what this column is, whenever we observe this, you will see that there's a maximum where the number jumps. And when that number jumps, that is the endpoint when we take the first derivative. So we can simply take the first derivative and simply look for the max point, and then from the max point, go straight along over to our sodium hydroxide measures, and that will become the volume at the endpoint. So there we have a way of determining the volume at the endpoint without having to go to the graph. Now, once I know that, then I can simply take 1/2 the volume at the endpoint, in this case 9.25, okay? And I'll need to then extrapolate from that 1/2 volume point over to my pH list, and I can estimate the pH at that 1/2 volume point. And the way we do that with this example is straightforward. So 9.25 is right in the middle, between 8 and 10. Okay, it's, approximately right in the middle. So what we'll do is we'll come over to these two values on our pH scale, and we'll need to, the pH that we need is going to be approximately halfway between these two. The difference between these two numbers is 0.15. 0.15. I got that by simply subtracting the upper number from the lower number, and I determine how many units they are apart, 0.15, meaning that the halfway point is about 0.075. 0.075 is the halfway point. And so I want to be just a little bit beyond the halfway point, as we were over on the volume side. And so I'll take 0.09 and add it to the upper number, which is a little bit more than halfway, and 0.09, then that would give me a pH of 5.96. 5.96 is a little bit more than halfway between these two numbers. And so therefore, 5.96 will equal the pH at the halfway point, and therefore will be equal to the pKa that we're seeking. That is the system that I want you to use. So the data that you have been sent includes the first derivative, the pH, and the volume. You want to, again, find the maximum on your first derivative column, go over to the volume column, and that will be your volume at the endpoint. Now the volume at the endpoint, we want to take 1/2, and then we want to estimate what the pH is at the 1/2 volume point. Okay? Now, so that's how we do the pKa. There's another bit of information that's in here that's important. So when we found the max, and you go over to the volume at the endpoint, you now use the volume at the endpoint to calculate your equivalent weight. The volume at the endpoint is the number that you will use to calculate your equivalent weight. And now if you go back and look at the example problem that I sent you, which is based on this information, you will now understand how to determine the equivalent weight using this number here. Okay, send me a message if you have any problems.